Hey guys, we're going to cover two sections again today, basically covering all the volume stuff. So volume of prisms, cylinders, cones, and pyramids. So we're going to do pretty much all of this. A lot of the individual volume formulas you can find on the MCAS formula sheet. I uploaded that for you. You can use that while you're doing this stuff. That's what you'll be given your sophomore year when you are taking the MCAS. But we're going to go over kind of the more general formulas, and let's just get right through it, see what happens. So for these units, we're going to be measuring volume. So volume is our three-dimensional unit. So volume is the total number of cubic units contained in the interior of a solid. Okay, so we're essentially just counting how many individual cubes, right, would fit into something. So for prisms and cylinders, these are going to go together. So what makes something a prism or a cylinder, okay, is that it has two congruent bases. All right. So in the case here, we have a rectangular prism. So you have a rectangular base on the top, a rectangular base on the bottom. For cylinders, you have a circle on the top, circle on the bottom. So those things are the same size. And then, depending on which one you have here, these have rectangular faces. Okay. So the sides of the prisms are all rectangles, okay? And the thing that is maybe less obvious is that actually the side cylinders actually have one side, one curved side that goes all the way around, and that's actually a rectangle as well. So even if you just took like a piece of paper like this, so if you imagine the ends of this were filled up with a flat side, so this would be a cylinder, kind of sitting like this. So if you slice through an edge of a cylinder, and you unrolled it, guess what? That is still a rectangle. Okay, so it's less obviously a rectangle, but it is. So these have two congruent bases, and they have rectangular faces. All right. And so the general formula for this, for the volume, is very simply capital B times H, where the capital B is the area of the base, and the H is the height of the solid. Okay? So remember, height is measured perpendicularly, so it's measured perpendicular between the bases, and capital B is the base. So for, in this case, right, so these really have the same, all of these have the same formula. Capital B, the area of the base times the height. In this case, we have a prism that's a rectangular prism. So that means that the area of the base is length times width. So that's your B. And this one is a cylinder. That means the base is a circle, which is pi r squared. So you get these. So when you look at the MCAS formula sheet, they'll have all these different formulas for volume. Okay? But really, they're all the same. So just knowing this one lets you do really any prism. Okay, so then we just throw at you something on this first example, which is a trapezoidal prism. All right, so on the formula sheet again, like trapezoidal prism is going to be listed separately from the rest, but these are all the same formula. The volume is the area of the base times the height. So for the trapezoid, so something like this, especially when I have bases that are odd, I'll kind of do my little notes off to the side. So I'll actually redraw my base. So this is a trapezoid. The long side here is 14, the short side is 6, and this distance here is 3. Okay, so we need to know the area formula for a trapezoid. So that is 1/2 the sum of the bases times the height. Okay, so this is where you need to be a little bit careful in that this h here in this formula and this h here in this formula are not the same. Okay, this is the two-dimensional area formula. Okay, so this is you looking at this two-dimensional shape. So this is the height of the two-dimensional shape. So this h is this 3. Okay, it's the height of the two-dimensional shape, dealing with this two-dimensional area. This h is in the volume, so this h is the height of the solid. The bases are the trapezoids, so the height of the solid here is 5. Okay, so this is why I like to do these almost like totally separate problems. All right. Also, you have capital B, which is the base of the solid, and in almost all, in a lot of the two-dimensional area formulas, you'll see the word base again, because here a trapezoid actually has two bases, two parallel bases. So this area is 1/2 the sum of 14 and 6. This whole thing ends up being like 30. All right. So now I can plug that back into my volume. The volume is the area of the trapezoidal base times the height. So the volume is 150. The units are centimeters cubed. Okay. For the right cylinder, this is one that we already know, right? So for cylinders here, you have area of the base times the height. The base here is just a circle, so it's pi r squared times h. That's going to be pi 9 squared times 6. So multiply that stuff out. This will give you 486 pi cubic feet. So this is your exact answer. If you wanted the approximate answer, you just plug that in and get a decimals. This is 1526.81. Right? So depending on what the situation calls for, either an exact answer or an approximate answer. Awesome. So the one weird thing from this, a lot of this section shouldn't be too bad because it's all very just like formulas, plug and chug, nothing too bad. This is the one kind of weird part, and it is Cavalier's principle. So I'll give you the kind of definition of this, and then I'll talk about essentially what it means. So what we have here is that if two solids have a couple of different things in common. They have the same height. Okay, so you see here, say all these things have the same height. Here, h, from the top to the bottom, between those two black dots. So if two solids have the same height and the same cross-sectional area at every level. Okay, so cross-sectional area is like this kind of colored plane. If you slice that through, they're saying capital B here, so the area of this square is the same as the area of this square, is the same area as this oval. So it's just kind of structured in a way that those things are the same. So if you have the same height and the same cross-sectional area at every level, so all the slices that you could take horizontally, all right, then the solids have the same volume. Okay, so if you have the same height and then the same slices, the same area slices everywhere you go, then the shapes all have the same volume. So the volume of that is equal to the volume of that is equal to the volume of that. All right, so that's Cavalier's principle. Now, the key to Cavalier's principle that we're going to primarily be using is the idea that's kind of demonstrated within these first two shapes, okay, which is that the volume for oblique solids are just kind of the slanted ones. Okay, so this is an oblique prism. All right, this is a right prism, so it's right because it's perpendicular to the base. The sides are perpendicular to the base. This is oblique because it's kind of tilted. All right. So the main idea here, the main reason for us using Cavalier's principle is for this. The volume of oblique solids is the same as for right solids. Okay, so all the volume formulas that we have are for right prisms, right cones, stuff like that. This allows us to use the same right prism, right pyramid, right cone formulas for things that are not right, for things that are slanted, for things that are oblique. Okay, so what does this look like? So we're going to find the volume of this oblique cylinder. All right. So this is a perfect case for Cavalier's principle. So this cylinder, okay, it has one base here, one base up here. The whole thing's kind of tilted. All right. So Cavalier's principle essentially lets us look at a right cylinder like this that has a radius of 4 and a height of 7, and essentially tells us that this volume is equal to this volume. Okay. Hashtag Cavalier. Okay. So even though this looks like a much more complicated shape, the volume is still area of the base times the height. The tricky part here is like the 7 here is the side length of this. Here, if I gave you this slanted length, that is not the height of the cylinder. Height is always measured perpendicular. So if there's something is oblique, you just want to be careful that you're actually not using the side length anymore. You're using the actual height. Okay. So the volume here is the area of the base, which is pi r squared, times the height, which is 7. Okay. So this ends up being 112 pi centimeters cubed. All right. And if you're looking for the approximate answer there, that is about 351.86. All right. So for this part here, you can pause the video, try these, and we'll double check back with them in a second. This is a great one, right? So for number 4, this is another Cavalier's principle. The volume here is still the area of the base times the height. And like I said before, just kind of redrawing the base is helpful. So this is made up of 2 right triangles. This is side of 9, side of 5. And the area of this triangle is 1/2 base times height. So again, this is the base and height of this shape. This is like we're on like a little side quest here. Okay, so this is kind of like in its own world. So the area of the base here is 1/2. The base of the triangle is 9. The height of the triangle is 5. So we get B is 22.5. So the volume of the solid is the area of the base, which is 22.5, times the height of the solid, which is how far apart the bases are from each other. And that gives us 180. Whoops, this should be meters cubed, not centimeters. Meters cubed. Okay, and now this one. This is a wild-looking shape. Okay, there's a couple things you could do. You could do 2 different volumes. So the volume here is the volume of the triangular prism minus the volume of the rectangular prism. Okay, so you could find 2 different volumes and subtract them, right? But what happens here is like the height of the triangular prism, because now this is the height here, okay? Because the bases are in the front, it's like in the foreground and the background, and the height is measured perpendicular to those. So the height is now this part going back and forth. The height of the prism is not this going up and down. The height of the prism is the distance between the bases. And the bases are the congruent pieces. So here you have this weird triangle with a hole in it in the front, the weird triangle with a hole in the back. Those are your bases. So instead of looking at it as a triangular pyramid prism minus a rectangular prism, you could just look at it as a prism whose base is the weird triangle with a hole in it. So you have triangle with a hole in it, prism. So it's just the area of that shape, the area of that base, times the height. So the base is the area of that triangle minus the area of that little square. So these have a side length of 3. The base is an equilateral triangle with side lengths of 10, which means I can drop in an altitude, make that a 5. And we know that this is a 30, 60, 90. So the height of this is 5 root 3. So the area of the base is the area of the triangle, which is 1/2 base times height. So it's 10 times 5 root 3 minus the area of the square, which is 3 squared. So the area of the base is going to be 25 root 3 minus 9. So you could just find that. And then the volume is the area of the base, which is 25 root 3 minus 9. Whoops. Didn't mean to close that parentheses. So 25 root 3 minus 9 times the height of the prism, which is 6. So the exact value, when you got to distribute the 6, the exact value of the volume is 150 root 3 minus 54. And the units here are feet cubed. And if you want, you could plug that into a calculator. You get approximately 205.81 feet cubed. Okay. Now, pyramids and cones, okay, have kind of a very analogous situation to prisms and cylinders. So what makes something a pyramid or a cone? The main thing here, the main difference is that these have just one base. Okay, so pyramids and prisms and cylinders have the 2 congruent bases with all the lateral faces. These all have one base and all of the sides are connected up to a point. Okay. And then the same thing, and then for pyramids here, cones just have a circular base and go up to a single point. Pyramids have lateral faces that are triangles. Okay. The lateral face of a cone doesn't unroll into a triangle because it has this kind of curved bottom. It actually unrolls, strangely enough, into a sector, into like a fraction of a circle, which is pretty wild. What you could do if you have like an old crappy birthday hat, the little crappy ones with the little string that snaps off and hurts you, take one of those birthday hats. You can just kind of slice through one of those. You can kind of see that for yourself. So the general form of the pyramids and cones, very similar. It's the same thing except it's precisely 1/3 of the area of the base times the height. Okay, there's some neat kind of GIFs of like demonstrating that. I'll probably try to find a couple and put them online with this assignment. I hadn't done that yet, but that's a good idea. So again, B is the area of the base, and H is the height of the solid. So again, not the slanted part. It's called the slant height. Okay, it is still measured perpendicular to the base. So if this were a square pyramid, the volume is 1/3 area of the base times the height. So if this is a right square pyramid, the volume is 1/3 s squared h. And here the volume is 1/3 area of the base times the height. So the area here would be 1/3 pi r squared h. Okay? Cavalier's principle still applies here. So if you have oblique pyramids, oblique cones, it's the exact same formulas. Okay? Select example here. You're using a funnel shown to measure the coarseness of a particular type of sand. It takes 2.8 seconds for the sand to empty. Find the flow rate in milliliters per second. So the volume of the cone, first of all, is 1/3. Area of the base times the height. Because it's a cone, the base is a circle, so it's pi r squared. The height of the cone here is 6. So the amount of sand that can fit in here is 32 pi centimeters cubed. Okay, so the flow rate, it goes through 32 pi centimeters cubed of sand per 2.8 seconds. But we want the answer in terms of milliliters per second. We have centimeters cubed per second, so we need to convert centimeters cubed to milliliters. Luckily, metric actually kind of makes sense in a gajillion ways. Okay, metric is fantastically easy. 1 milliliter is equivalent to the volume of 1 cubic centimeter. So it means if I set up like a ratio, 1 milliliter is equal to 1 cubic centimeter. Then just the units of cubic centimeter will cancel, and you just multiply that out, and this will be about 35.9 milliliters per second. Okay, so again, some of these can get a little tricky. Make sure you're just kind of off to the side calculating what the area of the base is, and then they're all either, if they go up to a single point, it's 1/3 area of the base times the height. If there are two congruent bases, okay, it's going to be just area of the base times the height. So it's just a matter of whether it has the 1/3 or not. Again, the hardest ones that you could run into, probably prisms or pyramids that have the trickier things, like we just did, the area of regular polygons. So you could have, say, a regular hexagonal pyramid where your capital B is going to be a regular hexagon, where you're going to have to use that 1/2 perimeter times the apothem formula. Okay, so stuff like that. So it can get a little bit tricky with how things are intertwined, but those are the basics. Good luck.